Hello, everybody. This is Aaron Schwartz, one of the secondary specialists in Montgomery County Public Schools. This video is called What is the Same? What Can I Eliminate? And the goal is introducing linear combination through reasoning. In Unit 2, Topic 3, students use systems of equations and inequalities to determine combinations included in solution sets. The key ideas include every point on the line represents a solution to that equation. A point in common for two lines is the only solution shared by the lines. Points of intersection can be determined by eliminating a variable and solving for the other variable. Some of the helpful skills that students have previously learned include proportional reasoning with integers and rational numbers. This is done in Math 6, Math 7, and IM. Students have also learned to solve single variable equations. This is done in Math 6, Math 7 or IM, Math 8, and it's done early in Algebra 1. There's a lesson sequence in the algebra curriculum called Can You Get to the Point 2? We're going to be introducing linear combination. Now, introducing linear combination, or the elimination method, without contextual parallel leaves the concept abstract and absent of meaning. To better illustrate the concept, we will ask students to consider the menu to the right. We may just give students this menu and ask them to record their observations and their conclusions. Some of these may include that there's one extra muffin in the second order. The second order is more expensive than the first order. Students may gravitate towards the fact that the second order is two muffins and two coffees exactly. And other observations may be brought up by students. But some students may need some scaffolding to help focus their observations and conclusions. So consider asking students, what is different about the options? They may then say, well, there's a difference in price, and there's a difference in the number of muffins. From there, we can ask students, how much more is one extra muffin? After all, the only difference between the two orders is that one muffin. So when we added a muffin, how did the price change? In this case, adding a muffin added $3.25 to the total cost. What is the cost of two coffees, or of just one coffee? Well, now that we know the cost of one muffin, we can use that to determine the cost of two coffees. We can substitute in that $3.25, and we can determine the price of a coffee. At this point, it's useful to ask students to build two linear equations. 1m plus 2c equals $6.25. 2m, or 2 muffins, plus 2 coffees, 2c, equals $9.50. From here, we actually want to ask very similar questions to what we used in the context of the menu, but replace muffins and coffee with variables used in class. Before, we asked what is different about the options, how much is one extra muffin, what is the cost of just two coffees and of just one coffee. Let's replace these with very similar questions about the variables and the constants in the equation. What is different about the coefficients and constants in this equation? How does an extra m change the constant? What if you removed one m? What is the value of 2c? Of just 1c? And from here, we can launch into the actual procedure because students now have a context for why they're doing it. Let's look at it again, and let's look at the actual procedure. We can use the symbolic representation to explain the process in which we just engaged. We start with our system of equations, and we talk about how we found the difference between the two orders. Since difference is subtraction, we can just subtract the equations as we would any other problem. We can eliminate what's constant, what is unchanging, what is the same in both equations. And we can find out that that one muffin was an extra $3.25. We can substitute in and find the cost of 2 coffees, and then the cost of just 1 coffee. And because we were able to reason our way through, we know that a muffin is $3.25 and a coffee is $1.50. This is key. What we've just done is we've used reasoning to solve the equations first. But the reasoning is then a support for why we take those procedural moves when we're looking at a system of equations outside the context of a scenario. But there are other ways to examine the muffins and coffee. Some students may perceive the situation differently. Some students may notice that half of the second order is 1 muffin and 1 coffee, and it will cost $4.75. They may have noticed this by noticing that they have 2 of each and they can eliminate 1 of each, cutting the order in half. From there, students may notice the third option is $1.50 less expensive and has 1 less coffee. So the coffee is $1.50. Using the third order, they can subtract a coffee to determine the price of a muffin. $4.75 minus $1.50 is $3.25. What the students have done procedurally in this version of the problem is they've used a scalar, in this case 1/2, to create a third and new equation that they can use to solve the problem. This is key to introducing elimination with a multiplication step. Let's look at a slightly different example. Introducing multiplication step adds another layer, but again, with contextual foundation, students will understand why to do it. Ask students about the menu to the right. Students may notice that they have 1 muffin and 1 juice for $3.25. They may notice that they have 2 donuts and 3 juices for $8.50. Just as before, some students may need scaffolding to help focus their observations and conclusions. Consider asking students, what is the cost of 2 donuts and 2 juices? And how can you determine that price? Doubling that first order gives us $6.50. How much more is 1 extra juice when compared to that order that has 2 of each? We can now observe that our new equation that has 2 donuts and 2 juices is very close to what the second order is. It's just missing a juice. Or another way to view it would be the lower order has 1 extra juice and 2 extra dollars. So we now know the price of 1 juice. And now we can determine the cost of just 1 donut. To do this, we can go back to our original equation. 1 donut, 1 juice, $3.25. We know that that juice is $2, so the donut has to be $1.25. Let's take a look at the procedural math, and let's tie it to the reasoning in which we just engaged. $1, 1 donut, plus 1 juice is $3.25. 2 donuts plus 3 juices is $8.50. We can double that first order. And now we get 2 equations that are very similar. In fact, the only thing that's different are the juices and the prices. We can now conclude that one juice is $2. From there, we can go back to our original equation, but instead of one juice, we can represent it with $2. We can deduct that $2 from both sides, and we find out that one donut is $1.25. So a juice is $2 and a donut is $1.25. The key here is that by reasoning our way through, we gave students the opportunity to understand why they would do a multiplication step. They could understand that the multiplication step gives them something that is the same in both equations, and therefore it's easier to compare what's different in the two equations. I hope that this video helps teachers create classrooms where students explore math, observe patterns, and develop conceptual understanding. If you have questions, comments, or have a video idea, please email me at the address below.